Hello again, now in the second part of this lecture. After we introduced a few terms in the first part, we are now able to introduce different sparse matrix schemes. As we've seen already in the MATLAB example, and where we applied the Cholesky decomposition, we introduced the expression fill-in. When we do the LU decomposition, Cholesky or Gauss decomposition, we have to eliminate the entries below the diagonal. If we are doing this in this situation, given for this matrix, we have to multiply the first row by a non-vanishing scalar and add this to the third row and then the second row to the fifth row and so on. So we're doing this here. Yellow means that this entry now is 0, but for the decomposition and afterwards applying the decomposition for solving a linear system, we need these factor, which usually the Lij in the matrix. And these are modified entries. In the situation that here was 0, there will be no modification here, but in general there would also be a modification here. And we continue eliminating below the second diagonal entry. So this will be 0 and we have additional fill in here. Continue also modifications, and also modification here. So we get fill-ins if we only consider the lower diagonal part. Not everywhere, it's behind the first entry in the row. So for a more general matrix like this, we see the fill-ins of the matrix L, of the LU decomposition, is right from the first entry per row, and for the matrix R, which is in some sense transposed, we get the fill-ins below the element with the smallest row entry. So think about that the right part is in some sense the transposed structure of the L matrix. Possible entries we will get or fill in the envelope or Hülle in German, which is defined the following. So we have some Fi of A. This is the column index of the first non-zero entry in the eth row of our matrix A. Our assumption that we have non-zero diagonals and the LU decomposition will be possible. And the envelope of A is a set of column indices that lie between first non-zero column index and the diagonal in each row. So where we get possibly fill-ins. So if our matrix is symmetric and positive definite, the Cholesky decomposition exists without permutation. It will be enough to store the diagonal and the lower part. We have the usual decomposition of Cholesky L times L transposed, or a decomposition LD times L transposed, where in this situation the diagonal entries of L are all 1. It's similar to the Cholesky decomposition, but then the square root of L is taken and these matrices L and N transposed are scaled. The advantage of the later one, L transpose, is that we don't have to compute the square roots. Nowadays it's not that expensive, but nevertheless we have direct access to the diagonal entries, and sometimes for some methods some kind of advantage. How to store a matrix in the skyline format. Let's assume we have the following matrix where we have these green diagonal entries and per row the yellow, the blue, the purple and the red entries. How to store? So we start with the first with the second row, index 1. See here we are indexing starting with 0 instead of 1. But in the second row, that's the first row where some non-zero entries may occur. If we just store the symmetric part, we have the 4. Then in this third row, the first entry, which is non-zero, is the 12. We store the 12 and the 0. And then the fourth row, the first entry, which is non-zero, the column index less than the diagonal, is only the 89. And then the last row, we have 4100. So that's the off-diagonal entries we store. We mentioned already that we assume that all the diagonals are non-vanishing, or that we store the diagonals separately, are given here. And then we also store the first entry of a row which is non-zero. So it's pointing to 0 for the second row. It starts with index 1. So again, we have to have 0 indexing. So 0, 1, 2, 3, 4, 5, 6, 7. For the purple colored row, it starts with 3. And for the red colored main row, it starts with 4, and the last, which is the end, is with 7. The question now is how we get the index where the row starts. So the 4, here it's 1, here it's 1, there's or this index 0, indexing 0, 0, 2, and 1. We can get it direct from our first column index. We know, okay, we have all the entries from 0 as long as the index is less than 1. Here we start by 1 and we increase the index so long as the index is less than 3. So we start with 3 as long as it's less than 4. And we know, okay, then we have only one entry, and starting from the diagonal, it's only one entry. So here we start from 0 to 1, so it's only one entry. That's, of course, we start here, we start here, and so on. So the length for each part per row is given indirectly from the column index vector. So what about the space complexity? Space complexity is an expression which defines the minimum number of bytes needed to store a data structure in a computer. It's not that complicated, beside the fact that we have these calligraphic B of theta, which is the minimum of numbers 8, 16, 32, 64, and so on, a power of 2 by factor 8, which is the amount of bytes we need to store. So it's not arbitrarily, not continuously, so it's the number of bytes to store a number, where we used zero-based indexing. So using this term, the minimum number of bytes we need to store a matrix in this sky format is, okay, we have the size of the envelope, so the amount of entries, which are possibly entries for by fill-ins by the LU or Gauss decomposition, and we have the entries on our diagonal, which are n. So this is the amount we have to store just for the matrix. But then we also need additional amount of storage for the indexing. That was, okay, for each row we have n entries, and then the pointers to where our row will start. Let's go back. So it's this index, so it's not correct, it's n plus 1. But there we have to store the number here, which we need is how many entries we have in this vector, which is given by the size of the envelope, was given here. So the next format, which is quite common, but depends on, it's not general, it's not useful or quite efficient for every sparse matrix, is a format where we store diagonals of the matrix. It's a simple structure. If the diagonals are close to the main diagonal, and we have only a few zeros on our diagonals, it's quite efficient. The advantage is we have long rows and a simple structure. How does it work? So starting with this example here, we take the sub-diagonal, the diagonal, and the super diagonal. We store everything. So given here, this is the diagonal. And from the sub-diagonal, we have an additional entry. So all the diagonals we store, by vectors of length n. And we didn't need the additional information for the shift vector. So -1, 0, 1. Now, if you multiply your right-hand side by the matrix by the right-hand side, always multiply one vector by the vector. If you multiply this matrix by a vector x, and now consider only this diagonal, you multiply 1, 1 by x0, or x1, 2, 2 by x2, 3, 3 by x3, 4, 4 by x4, and so on. If you multiply the vector on the right-hand side by sub-diagonal, you just shift the vector. So usually you multiply then x1 by this entry, you multiply x2 by this entry, you multiply x3 by this vector. So now you start your computing loop. You multiply this term by x1, x2 by this, x3 by this, x4 by this, x6 by this, and so on. And the other way around, if you multiply your vector given here by x1, 2, 3, 4, you multiply x2. So your index for xi plus this shift vector. And this can be easily done, and the computation is, if you have long vectors, quite efficient. The space complexity for this matrix is in some sense quite good. So if G is the number of non-zero diagonals, and if you have only a few zero entries on the diagonal, this is only a little bit of overhead. But then you store n times d for your diagonals, and just for indexing the shift vector, which is b 2n minus 1, the 2n minus 1s is obvious. If you have an n by n matrix, you have in the shift the term 0 up to n, but you also have the minus indices, so that means you have n plus n minus 1, which is the 2n minus here for the index. The next example of a basic matrix storage scheme is the LPAC scheme. Here we again try to get long vectors to be efficient. We do this by shifting all entries to the left, so that we get these green and the entries for the second entries per row, the column with the third entries. But we also have to store the column index. So this can be done in this way. You store, let's say here, negative values where nothing is stored. And from this two vectors or arrays, values and column index array, you build up a long vector. So concatenate this blue behind the green vector, the red vector behind the blue vector, and the yellow behind everything, and also the column index, and then give these two vectors to your multiplication advice, and then you get very fast matrix vector operation. Sorry, I missed this, and that's quite efficient if you have long rows and long vectors, but the size, as you see already here, you should not vary too much. So all rows should have the same size that you will get an efficient method. So another well-known storage scheme is the jagged diagonal storage. It's a modification of the LPAC format. Here we see there's a lot of zeros in between, which is not a real advantage. So why we just permute the rows in such a way that we at the end we only multiply with non-zero entries. So we have the disadvantage multiplying by zeros, but probably can take some advantage by the additional, if we add the additional work of permuting the rows. This is done by the jack diagonal storage. So starting with this matrix, or let's do on the next page. So we have this matrix given. We shift everything to the left, the same as for the compressed diagonal storage in some sense. And additional, we also store the indices for the column. The next step, which is additional to the method before, we get some calculate some permutation such that first we have the longest rows first, and then we have this row and this rows, and at the end we build a long vector so that again we have this vector, put these vector below and this below, and the same for this and this vector for the matrix entries and the column index, and we pipe these vectors with this permutation vector or with a permuted vector we have to multiply with to the multiplication device and get in a quite efficient way the result. Sorry. Yes. A more general scheme is the coordinate storage scheme. It's obvious if you have the easiest one probably. If you store a matrix, a sparse matrix in a file, in which way would be the easiest to do this? Of course, you would store let's say the matrix is given, you would store 3 with index 0, 0, you would store 4 with index 1, 1, and then you would store the 19 with index 2, 0, and so on. And of course, the way, the ordering, how you store the matrix entries, it's not necessary. So it could be that you store in such a way that the 31 is the first place in the data, but you also have to store the row and the column index. So these data in this way are given. The ordering is not necessary, and even the situation could be arise that the 3, which if you multiply, of course, you have to multiply the corresponding first entry of the vector you would like to multiply with 3. But it could be also that you double the row and column indices. Let's say you have again 2, a 0, and 2 here, but then the 31 could be split into 29, and here the entry would be 2. And in some sense, you will get the same result if you do the matrix vector multiplication. That could be also occur for the finite element method if you don't assemble the matrix, if you just store the submatrices. You will see later what I will mean with this idea. So, a few comments about the space complexity. Let Z be the number of non-zero elements of our square matrix of dimension n times n. Then this space complexity is, of course, we have Z entries, and for each entry we have to store the data itself, and we have to store the indices. And the indices will be, the row indices will be between 0 and n minus 1, so that's b of n, and that's 2 times for the row and the column index. What about the matrix by vector product? It's easy if you just initiate the solution y, and then you have, I'm sorry for that, that should be k. So you start your k you go from k equals 0 for all non-zero elements. In the three vectors, the vector for the matrix entries, the vector for the column index, and the vector for the row index. And then this can be easily done element per element. The question now is the most efficient way to store a matrix. If the indices are small, of course, then these numbers are small. On the other hand, in the worst case, you will end up that you have a matrix of Z entries, but you need 3 Z storage places, which is quite expensive. So from the point of small overhead due to this storage scheme, this coordinate storage scheme is quite expensive, but there's no free lunch. So. But on the other hand, it's easy to append an entry if you have the correct storage schemes or allocating and resizing a vector, but it's more or less doable in capital O of 1. Changing and deleting matrix entries or a whole row, it's quite time consuming. Therefore, that's a more advanced but also general scheme, which is the compressed sparse row storage scheme, explained in the following. So again, we store the non-zero entries row-wise and shift everything to the left. So first the rows, then the blue, then the green, then the yellow, and the purple ones. Of course, since we shifted row-wise, we need the column indices which we store, but we have done some ordering, so we know where the first row starts, we know where the second row starts, we know where the third row, and so on starts. And from this data, we can recreate also the row index, or starting with the row index and then continuing with the column index. The advantage is that before with the coordinate system we have z times 2 times b of n. Now we only need a smaller one, only n plus 1 times some index. Instead it was z times b of n. Now we have n times b of z. But in general this grows only logarithmically and not like n, which is here linearly. So from the point of storage, we have need less storage compared to the coordinate system. But the question may arise: is it quite easy or difficult to change the coordinate or to change the storage scheme? Before we mention the transforming from one form to the other is the matrix vector product with a CSR matrix, and similar to the matrix vector product with the coordinate format. Here let's go loop over all rows. For each row, the result for each row is xj was set to 0, and now the column indices are given by k. We start the row, once again, so the row indices will be stored in the places from the row pointer j up to the row pointer j plus 1, as long as the k is less, and the column index itself is given by the column index vector, known from place k, the value from the long vectors, and this is stored to the jth row. As I mentioned before, a few comments how to convert a coordinate system or coordinate matrix stored in a coordinate matrix to CSR format. Given this matrix, and in coordinate format, these values are given in such a way, and here we store the row and the column index. How we proceed to get the CSE format. Therefore, we first allocate the memory. Memory is similar, so this will be the memory for storing the values. It will be the vector for storing the column index, and this will be the row pointer. And we need some work which is more or less the size of our pointer size. So that's, if the matrix is n times n, this would be n plus 1, this would be n, and these both vectors of size z, the number of non-zero entries. After we allocate the memory, we just count the entries who will end up per row in such a way that we increase in our additional work vector here. Each time we pick the row value, we increase this value by 1. So here it's 0, we increase by 1. Here it's 1, we increase by 1. Here it's 2, we increase. Now it's 3, we increase. Now it's 0, we increase the first entry. The next row index will be 1. Then we have again 1, and then we have 2 that will increase 2. In the next step, we build the cumulative sum. So 2 plus 3 gives 5, plus 2 gives 7, plus 1 gives 8. It's given here, and copy this to this row pointer vector. Now this gives the entries where we can store where the row will start. So the row will start at the place 0 because we know, okay, there's nothing before 0. The second row will start by 2 because we know that in the first row there will be 2 entries. For the third row will start at 5 because we know we have already 5 entries we counted before. And that's what we're doing now. So we copy the values corresponding to the row vector at the right place. So we start here with the first entry. We have the 11. The column index is 0, and we start here. And we see before we increase this in this element. Next one would be 21. It has to be stored in the first row, so that means, okay, we start by 2. That will be increased, and we also store the 0. So it's given here. Next would be this one. We have the 32. 32, it belongs to the second row, and we have the index 1. So the second row starts with 5, and again we have the column index 1 copied. The next would be 44. 44 will be stored to the last entry, and we have to also copy the column index again here, 7 to 8. Then next will be starting with 13, and you see also where storing the 22 in this place, and we increase this one. Then we store the 24 at this plan, and we increase this one. Again, we have to store the 33, and we increase this one. So, and that's it. At the end, we have to shift this vector to the right, or copy this once again and renew this to 0. But we end up update the row vector. This is now, these 3 vectors are the result of the conversion from the coordinate format to the CSR format.